I know there's only about 10 or so minutes left, so I'll try to keep it quick.
You have
But
about 20 minutes. We'll probably run 10 minutes over. It's okay. Go ahead.
okay, sounds good. And also a lot of this work is an overlap of Mark's work, and a lot of this is uh, so there's parts that we can definitely gloss over here. So this work is done in collaboration with Laura Graves and Dhananjay Ashok, and under the supervision of Vijay Ganesh. um, Deep neural networks have been successfully applied in many fields. We've had quite a few talks here about them already. Especially, this has led them to be used in safety critical settings, such as controlling autonomous vehicles. As a consequence, there is a need for these testing, analysis, and verification tools that are um, tuned or specialized for these DNNs. So we wanted to start off with this general definition of a problem that all of these DNN TAV tools are designed to solve. And we call this the DNN SAT problem. So the DNN SAT problem goes as follows. Given a DNN model M, a label Y, and constraints phi, which are over the inputs, the parameters, and the outputs of the model, determine whether there exists an input X to M such that M labels X as Y and phi holds true. While this is simple, you can imagine that we can encode many types of constraints here. And in the next slide, I'll give an example. So a couple of things. One, these constraints are designed in such a way that satisfying the constraint leads to property violations. And two, we don't necessarily need to look at this as a decision problem. It can be thought of as an optimization problem, especially in settings where constraints phi may never be completely satisfied. So an instantiation of it, concrete example is adversarial robustness. And Mark gave a definition of it earlier, so I'm going to keep it a little quick here. But essentially, adversarial robustness is the absence of where adversarial examples. And here, I'm using the definition by Zico Coulter and Alexander Madre for adversarial robustness. There can be different ways you can define adversarial examples, but we're using one of them here. So in order to formulate this DNN SAT problem for adversarial robustness, we would include an input X and make an assertion or check whether the model M labels X as Y. And in addition, we determine whether there is an additional input Z such that the model M does not label Z as Y, and the distance between X and Z is less than some threshold delta. Now, this distance function can be dependent on the type of domain. So for example, in the case of vision, we often use L infinity distance or L2 distance, or in the case of natural language, you would use something like cosine distance or edit distance. So now that we've defined the problem that the DNN SAT TAV methods or the DNN TAV methods are aimed to solve, let's look at some properties that an ideal TAV method would have. For one, it should scale well. It should scale to industrial-sized DNNs. Industrial-sized DNNs like GPT-3 use hundreds of millions of parameters, and most tools currently do not scale to that. Two, it should not establish restrictions. DNNs use many different types of architectures, many different types of activation functions. So ideally, we would want to be generalizable. So we'd want it to work on all, if not all, at least most DNN architectures. Three, we want it to express any property of DNN that can be tested. There's been a lot of research finding new vulnerabilities of DNNs, such as their vulnerability to unfair behavior or their vulnerability to bias. So it would help to have a TAV method that can express all of these properties as needed, instead of having to design a new TAV method for each of these properties separately. And four, it should be both sound and complete. Again, sound definitely, but complete is a compromise that a lot of industry experts are willing to take, just because current DNN and TAV methods might not even scale. Saying all that, we can classify the existing DNN and TAV methods into the following categories. One, testing methods, and these methods are search-based methods, and they're searching for inputs that violate some property. They often use gradient information to efficiently navigate that search space, but they could also use fuzzing or genetic algorithms in order to search or test. These methods are very scalable. They can work on industrial size applications, but they provide limited expressibility, and they are sound, but they're not complete. The next category, we've got this verification program analysis-based methods. These methods encode the DNN model into some symbolic form, usually a system of equations or some SMT encoding or SAT encoding, and use a corresponding solver to either find inputs that violate this property or to prove that properties hold. They are expressible, but they're not scalable, at least the current ones. And they restrict the DNN architectures. Usually they restrict to the type of activation function used to just be ReLU or just have one or two types of activation functions. Reachability methods define an allowable region, often defined geometrically as a polytope, and they propagate that region throughout the network. So this output region encapsulates all the inputs possible from that input region, and they use that method in order to verify. They are somewhat more scalable than verification program analysis-based methods, but they are limited in their expressibility, and they also restrict the type of DNN architectures used. And depending on the tool, they can be, they are sound, and depending on the tool, they can be complete. So as a consequence, because there is no one method that is scalable and generalizable, so that does not restrict any architectures, while being expressible, we use what we're calling the constraint gradient method. And at its core, this leverages two existing works. The first one is this approach introduced by Mark in their work, Deep Learning with Differentiable Logic, that converts these logical constraints into differentiable loss. So we've got our own implementation of that, and we've encoded different kinds of constraints in addition. And two, we're using a modified gradient-based optimization method, specifically the modification of the fast gradient sign method by Goodfellow et al., in order to find inputs that satisfy these constraints. So the first two slides I'm going to gloss over very quickly because Mark and Vivek went over the use of Lukashevitz T-norm and why, how that helps convert these constraints into these differentiable loss. I just wanted to stress that because this output of these constraints is a differentiable loss, we can apply our gradient-based methods. And in practice, although I know Mark mentioned this as well, although this is differentiable almost everywhere, not everywhere, it's worked well for us, and we've had to do a few tweaks in order to make it work in our situation, but in practice, it works pretty well for testing. And again, a quick example, the standard adversarial constraint from before would be converted to this equation here, and it's in our case, it's converted to this loss function that is suitable for a deep learning platform, TensorFlow and PyTorch. Now that we have these constraint loss, as Mark mentioned, we can use different optimization algorithms to find examples. We've opted to use this fast gradient sign method because it's efficient. Specifically, what we do is we calculate the gradient of constraint loss with respect to the input example, and we modify that input slightly in the direction of decreased loss. So this is a very cheap computational calculation, and it's been used in many different types of adversarial attacks. So because this is not complete. We're not guaranteed to produce a solution, but we run this for multiple iterations, and we give it a fixed time. And in practice, we find properties. We find examples that violate these properties in most cases. So in order to test the efficacy of this method, we ran some experiments. We ran 3 sets of experiments, each using different constraints. All these constraints were using adversarial examples, but it doesn't. But you can imagine that you can test other types of properties as well. So the first adversarial example that we're looking at is the standard one, as given in the definition above. The second one, that we're calling natural adversarial examples, adds an additional constraint to the previous one. And this constraint states that the original label should now be the second highest classification. And the intuition behind this is that the neural network model would take this perturbed input and still have a fairly high confidence that it is on the original label, which is why it's still the second highest classification. However, it is still misclassified. And then the third example is flow adversarial example. And this uses work from Shao et al., where they're using spatial transformations instead of perturbing the pixels directly. They're moving the pixels around. So they introduce this flow loss, and which is what we've incorporated, just to showcase that many different types of adversarial attacks can be implemented using this idea, one general framework. For each of these experiments, we compared the CGD, constraint gradient descent method, against various TAV tools on 3 benchmarks. The first set of benchmarks use models from VNN-Lib. It's an initiative, international initiative by a verification-based team that are trying to provide these benchmarks for verification tools on DNNs. The second set of benchmarks we're calling robust models that are trained adversarially. So in order to see how these models, these attacks in order to see whether these attacks work well on these robustly trained models. And the third one is ResNet 18, which is a fairly large model. It has around 11 million parameters in order to see if these tools scale well. So for each of these tools, we give it a certain amount of time, and we record the time taken to produce a counterexample or provide a certificate of guarantee if it can provide that. And we are using par2 scoring method to calculate. Essentially what we're doing is if a method time runs out of time, we're penalizing it by adding twice the amount of time limit. So here are some of our results. So on the y-axis here, you see the par2 score. And each of these collections here correspond to one of the tools that we used. And each of the colors respond to each of the experiments. So blue is the standard adversarial example experiment. The red is the natural one, and the yellow is the flow. So from left to right, we've got constraint gradient descent here. Carlini and Wagner, which is a optimization-based testing method, a bounded iterative method, fast gradient sine method. These 3 are testing optimization-based methods. Then we have ERAN, which is a reachability tool. We have MIP Verify, which is a verification-based tool. DLFuzz is a testing method that uses fuzzing. Marabou is a verification method. Random fuzz essentially randomly fuzzes the inputs. And genetic algorithm, which is a testing-based method. And for standard adversarial examples, it's fairly clear to see that constraint gradient descent, along with the other gradient-based optimization methods, have a much better result. So here, the lower the score, the better, because this corresponds to the amount of time taken. And this makes sense because these tools are built for this. Whereas the reachability and verification tools work fairly well on the smaller benchmarks, but on the larger benchmarks like ResNet, they'll time out and they're penalized for it. In the case of natural adversarial examples, by default, the gradient-based methods don't allow for encoding that, and so they've timed out in all of these. Whereas the reachability and verification tools, you can encode that, but it does take quite a while, and they do time out a lot on the ResNet 18 models. And the flow adversarial example, currently as it stands, cannot really be encoded in the reachability and verification tools, and they're not able to be used directly in the other gradient-based tools. Whereas in the constraint gradient descent, by design, they're able to be used. And so we see some fairly great results here. So wanted to quickly conclude. So again, current DNN TAV methods can be divided into testing, verification, program analysis, and reachability methods. Each method has its strengths and limitations. And crucially, there is no one method that can scale well to the DNNs used in industry while being expressible for different properties. So we use this constraint gradient descent method that leverages the method of converting logical constraints into loss and use a modified gradient-based algorithm in order to find examples that minimize this loss. And we compare this against state-of-the-art tools on a collection of benchmarks and show that it is just as scalable and generalizable compared to state-of-the-art methods. Further, it can test for properties that current methods currently can't. And so it's easy. It's like a general framework where you can test for many kinds of properties as needed.
Thank you, Vineel. Thank you for a great talk. Some clapping for everybody. There are questions. I think, oh yeah. So allow me to ask a question or two here. You mentioned that the verification methods allow one to express a very large class of properties, right?
Right.
Do you know how the kind of constraints that you are able to express in your CGD method, how the expressive power is limited relative to, say, the verification methods? So in your case, I guess you have the constraints have to be in some sense differentiable.
Exactly. So I think, yeah, I think the main thing is that the constraints have to be differentiable. Now, for example, like the flow loss, spatial perturbations by default are not differentiable. But in the work of Shao et al., what they did was to come up with a differentiable way, like a relaxation where that is differentiable. So as long as we can come up with these relaxations, we may be able to express a lot more properties. Yeah. However, that is still the main limitation compared to verification tools.
Thomas, did you have a question? Did you have a question, Thomas? I thought you raised your hand.
Hello. Yes, very interesting talk, but I would like to, have a question for the second last talk. Maybe Gerhard, I can. To Mark. Mark, are you there?
Mark yes, I'm here. Sorry.
Oh, okay, good. Well, I really, well, the other talk was also very good. But I liked your try to be as far as possible a little bit more formal. You introduced to the concept of fairness, and I was wondering whether it is inspired by or maybe related to somehow to the formalism by, say, Cynthia D work. Do you know that?
No, I think I'm not familiar with that. I'm sorry.
Okay, Cynthia D. Maybe it's inspiring for you.
Yeah,
it's
I will definitely have a look. Thank you.
Okay.
So Vineel, I had a couple of more questions. One question was, where do you see this going, like constraint gradient descent based methods in terms of the kind of properties that you can test going forward?
Yeah, I think so. What we're looking at is how to apply this in other settings, like, for example, natural language. Oftentimes, the types of testing you can do in natural language is not as is quite limited, and there are no tools that can easily test for, let's say, all these different types of settings. Same thing with reinforcement learning models that use deep neural network controllers. So this can be a very general framework for testing all these different kinds of models, as long as you give the right properties.
You also tested adversarially trained models, right? And you were able to find adversarial examples against them. So what does that say about adversarial training as a defense mechanism?
So in those models, in general, those models were harder to attack for the gradient-based methods. However, they were still able to attack them. And I think that's just because the current adversarial defense mechanisms haven't caught up as much with the adversarial attacks. I think that's just an artifact of that.
Thank you again for a great talk.
Thank you.
It's fantastic. And thanks to all the speakers today for a fantastic set of talks. And this is going to be the last session of the SAT-SMT Foundations workshop. We had a phenomenal time organizing this, starting in February, and all of the talks are available online. This was co-organized with Antonina Kolokolova, Moshe Vardi, Marian Hule, Maria Bonet, am I missing somebody? And Kevin Layton Brown, right? Antonina, do you want to add few words and maybe an announcement or two regarding your regarding the session tomorrow?
Yeah, sure. First of all, thank you so much, everybody, for wonderful talks, and thank you all the attendees and participants for coming in for the semester. Really wish the semester were in person, but life interfered. So thank you so much for bearing with it in this strange world, in this strange format. For the SAT participants, so whoever else is interested, just send me an email. We are planning a town hall tomorrow, tentatively at 11 a.m. at the Fellows Talk time. And it's a town hall, kind of where to go from there, what to do next. So if please come, we'll chat, we'll see what to do, both science, logistics, and if you have some ideas, again, both science, logistics, please let me or Andrea know. Yeah, everybody is welcome.
So,
and I guess right now there is a tea time on Gazatown, right?
Yeah. Just to confirm, you are going to send out an email to the participant confirming the time and the method?
So I'm still waiting to get the Zoom link. I will send out the Zoom link as soon as I get it. And I'm also hoping to confirm that it won't clash with anything if it's at 11 a.m. But there should have been an email asking for ideas, things to talk about, what people want to discuss. That's kind of our last chance to get together as a program before the reunion and share whatever we want to share.
Do we have a date for the reunion?
We don't have a date for the reunion. I've heard rumors that if you really, really ask, we might be able to get a longer reunion, like a month-long reunion. So hint, if you have a venue like a survey where you could ask, that's one thing you could ask for. And hopefully a year from now, the reunion will be in person. It will be, I guess, sometimes next summer. That's how it's usually done.
Okay, so this is the last week for the entire semester, and thank you everybody for participating and contributing. So we'll see you soon in Gathertown and tomorrow at the town hall. Thank you.
Yeah, so Gathertown, we could go to workshop Gathertown, or better yet, to the people who are program participants to the internal Gathertown. Should I post a link?
Yeah, maybe you should do
Yeah, let me do this. Okay, I'll post the link to the workshop Gathertown, but I think most people will be on internal.
All right. Thank you, everybody. Bye-bye.
Thank you, everybody.